commenting there may be a word missing there.
Yeah, it refers to those formulas.
Oh, I see.
So.
Scattering amplitudes with Mark Spradlin.
Okay, good morning. So just to review where we were at the end of last time, we talked about the fact that three particle amplitudes are completely determined by Poincare symmetry, and we found that for the case of a spin 1 particle, say massless particle that comes in two flavors having two types, helicity plus or minus 1, the 3-point amplitudes are uniquely determined up to overall coefficients. I left these boxes here to say something more about those overall coefficients in just a second. We found that a single or even just two particles of this type can't possibly have any self-interaction. You need at least three of them labeled by particle types A, B, and C here, and that the coefficients that appear here need to satisfy the Jacobi identity in order for a 4-particle amplitude to consistently factorize. Okay, now I want to say something very simple about dimensional analysis, because this is another useful criterion. Oops, wrong chalk. Dimensional analysis, that will tell us at least what the dimensions of those coefficients should be that I've left undetermined in the boxes. So there's an exercise in 4 dimensions, a scattering amplitude of n particles should have dimension of energy to the power n minus 4. Sorry, 4 minus n. Okay? And so the way you do that is you take this scattering amplitude, you square it, you integrate it over the n particle phase space, and you should get an area. That's what it means. I mean, that's how you construct a scattering cross-section from an amplitude. Okay, so if you do that exercise, you'll find that an n-particle amplitude should have energy, dimension energy to the 4 minus n. Now, our brackets here each have dimension of energy. The way to see that is remember the main formula. I should have written it here. The momentum 4 vector factors into the product of spinor helicity variables in that way. So each of lambda and lambda tilde has dimensions of square root of energy. So each of these brackets has dimension of energy. Okay, so using that criterion, we can look at this amplitude. Let's look at this one, for example. And we immediately see that it has energy cubed on top, energy squared on the bottom. This has units of energy, so that's the correct unit. So here we need to put a dimensionless number. G equals dimensionless. On the contrary, here, this product has units of energy cubed, and so does the one on top there. So whatever coefficient goes here must have units of energy to the minus 2. So let's call it h, and then I'll write here. I'll continue down here. Well, I know I'm getting into the illegible zone down there, so I'll continue over here. G is dimensionless, but h has units of energy to the minus 2. Okay. G is the kind of interaction you get in pure Yang-Mills theory. Whereas this thing would have to be the coefficient of a higher dimensional operator, and in particular, this would would arise from if you had a term in your Lagrangian like f cubed. Okay, so in particular, the first and the fourth amplitudes here vanish in pure Yang-Mills theory. Okay. Now I want to do really quickly the analogous exercise of checking factorization for the 4-particle graviton amplitude. This is a fun exercise, and it's even easier than the case I did last time. Okay. Because we want to use factorization, let me first write down for you the 3-particle amplitudes. Now, a graviton is a spin 2-particle, so it comes in 2 helicity states, having helicity +2 or -2. It's conventional to denote the helicities by 2 minus signs or 2 plus signs. This kind of notation, unfortunately, doesn't extend to the case when you have fermions, because you can't have half a minus sign. Anyway, using the formula that I derived last time, you can immediately see that this amplitude has to be 1, 2 to the 6th over 2, 3 squared, 3, 1 squared. And this is an opportune moment for me to comment on something that I did say in yesterday's lecture, but I certainly didn't make it clear enough, as was evidenced by several conversations I had with students after the lecture. Remember when I derived the general form of the 3-particle amplitude, and I said that it smelled the same. I confess that my statement was even stronger. I said it was entirely analogous to the way you derive a 3-point function in conformal field theory. That's not quite true, because there's an important distinction, which is here it's important that we be able to allow ourselves to independently rescale the spinor helicity variables of every particle. So in a conformal field theory, scale invariance of course only applies you have to rescale all the particles at the same time. So incidentally, by the way, there's no need for me to write the left-hand side of this formula. You can look at this formula and immediately use the little group scaling to deduce what the helicities of the particles are. So imagine we take, for example, lambda 1 to 1 over lambda 1. In this formula, well, we would get a factor. We get -6 powers of W from the top and -2 powers from the bottom. So altogether, this how did that become an omega? I'm sorry. Or W omega, whatever. If we scale lambda 1 to 1 over W lambda 1, then this amplitude scales with a factor of W to the -4. And if we recall the general rule that if you rescale a particle of helicity h, its scale is W to the 2h, we immediately see that this is a scattering amplitude that's appropriate for a particle 1 having negative helicity, helicity -2. Similarly, particle 2 has helicity -2, but particle 3 has helicity +2. Okay. Oh, up to an overall coefficient. Okay, now let's do our dimensional analysis exercise again. This thing has units of energy to the 6th divided by energy to the 4th. So altogether, this factor has units of energy squared. A 3-particle amplitude in 4 dimensions should have units of 1 over energy. So we need to put some coefficient here that has units of 1 over energy. And the natural candidate is the square root of Newton's constant. Up to a numerical factor, possibly. Okay, so these are the three graviton amplitudes. You could also contemplate the possibility, at least these are the 3 graviton amplitudes that arise purely from the Einstein-Hilbert action. If you added, for example, some higher power of r to your action, you could also generate the analogous graviton amplitudes for these helicity cases. But let me not do that for the moment. Yes?
Hey, Mark. So in this case, because G is dimensionless, you sort of, if you don't have something other than Yang-Mills, you can't contemplate the other ones. But in this case, I have a dimensionful coupling already, so why can't I just say from this point of view, well, the ones with all minus helicity, say, I'll build it out of whatever powers of G Newton I have. Is there any way I can see that I won't get it from Einstein
Okay.
gravity?
Should I repeat your question, even though it was very... Okay, so the question was... Here, the question was, here there was a qualitative difference because the G already had this was a dimensionless coupling, and so here you can't have the A. I argued that you can't have the H unless your action contains some higher dimensional operator. But here Oliver pointed out that already, I mean, you can't even have these couplings by themselves unless you already have some dimensionful parameter in your theory. So maybe it was too slick for me to argue why. Yeah, I just don't want to consider them. But yeah, generically a theory of gravity will have higher curvature corrections.
It's just not, I guess it's not obvious from this analysis.
From this
From
analysis.
Einstein gravity and what else.
Oh, yeah, that's the point. That's right. So I claim that's true, but yeah, I guess it's not particularly obvious. Well, no, but but if you had, okay, since I'm on that point, if you had this, now by the way, we should all be able to write this down without thought, right? We need something that scales like w to the minus 2 under each particle. The unique choice is this. This has units of energy to the 6th, so we need something here with units of 1 over energy to the 5th. So we would need here g Newton to the 5 halves, for example. So, but your question really is about how do we know that this coefficient of this is 0 in pure Einstein gravity? And yeah, I don't have a quick way to argue that right now. Okay, so anyway, let's now contemplate the same exercise we did last time. Let's consider factorization of a 4-graviton amplitude. So let's consider the amplitude A, 1 minus minus, 2 minus minus, 3 plus plus, 4 plus plus. And let's make a list of what we know about it. It must be proportional to g Newton by factorization. Right? This amplitude should have poles, and the residue of each pole should be a product of 2 3-point amplitudes. Each 3-point amplitude comes with a factor of square root gn, so this has to have an overall factor of gn. Yes, there's a question.
Shouldn't the 3-point amplitude there have the denominator?
Yes, thank you. Thank you. Yes, excellent. Okay. And thank you. And these are both squared? Yeah. Thank you. Okay. And then in the back.
Isn't it clear that in Einstein gravity, the 3-point amplitude has to be proportional to root gn just from the Feynman diagram?
I was having the same thought, but I hesitated to use the word Feynman diagram. It's kind of debasing. So, but indeed, if you just think about, if you just imagine expanding the Einstein-Hilbert action, that's all you would get. Yeah. Okay. I mean, as I said yesterday, you weren't here for my lecture yesterday, but already secretly, as soon as we go to this step here, so everything we say about 3-point amplitudes is non-perturbative, but as soon as we go to this step, we rely secretly on the crutch of perturbation theory, which means that secretly there's always an action somewhere in the background, even if we choose to forbid ourselves from looking at it. Okay, must be proportional to Gn. By little group scaling, Well, how about this? Let me write. By little group scaling, we know what prefactor to put. Now, that choice is not unique. Okay. Here are two different ways. There are many more. But here I've written on the board two different ways to manifest and implement the correct little group scaling that this amplitude should have. I don't need to consider this because this f prime and this f are related to each other by an overall factor that looks like this. Okay, so if you choose this factor and I choose this factor, then your f prime and my f will just agree with each other, will disagree with each other by an overall factor of s to the fourth. So I can absorb that into my definition of f. So let's put this all as an aside, and let's just agree that here I've made some choice that implements the correct little group scaling, and then we'll see what we can say about this function that can only be a function of the Mandelstam variables. Number 3 is by crossing symmetry. F must be symmetric in S, T, and U. And the fourth is F can have only simple poles in each of S, T, and U. Tree-level amplitudes can't have double poles. Yes?
Why should F be symmetric in ST and U? Shouldn't you only have one pole for equal cross-section?
I'm sorry, 1, 2. No, no. I see why you say that. Yeah, the question is, how did I so quickly conclude that it should be fully symmetric in S, T, and U when it appears that the symmetries of the amplitude only allow you to exchange 1 and 2 and 3 and 4? You know what? I don't even need that. It's true. It will come out to be true. I think it's true. Well, I know it's true because we'll see that it's true in just a minute, but let me put it in parentheses for the moment. Oops. Someone should have stopped me. Okay. That's going to suck later. Oh, no. Okay. I wish that had been my Easter egg, you know, instead of the phone call. Okay. Fortunately, it was never intended that you take notes on that formula. So the remains of the formula hidden below the chalk will suffice to make the point I intend to make when we get to that. Okay. So by dimensional analysis, let's look what we have so far. Okay, this has units of 1 over energy squared. This has units of energy to the 8th. Overall, this is a 4-point amplitude, so it should have it should be dimensionless. So F must have units of 1 over energy to the 6th. So the conclusion is up to an overall constant, F is 1 over STU. So with essentially zero effort, we've derived the 4 graviton scattering amplitude, which I assure you would be considerably more effort if you were to try to derive this from Feynman diagrams. In particular, notice that an interesting feature, any individual Feynman diagram you could possibly draw would only have one of the poles. If you draw an S-channel Feynman diagram, it would be proportional to 1 over S. A U-channel Feynman diagram would be proportional to 1 over U. It's rather remarkable that somehow all the mess of everything you get combines into something with this rather remarkable denominator here that's S times T times U. Rather non-trivial. Okay, are there any questions about this? Okay. All right, the next topic I want to discuss, so I've shown you some examples of 4-particle amplitudes for both spin 1 and spin 2. Now I want to discuss an important topic of recursion. And this is a mechanism which can allow you to rather efficiently derive expressions for any possible tree-level amplitude. And we'll focus at, well, modulo certain conditions, and certainly spin 1 and spin 2 do satisfy those conditions. So the idea behind recursion is the following. We imagine shifting our momentum twistor variables. So you start with some amplitude. And then you shift. There are a variety of ways you can choose to do this. You just do a simple shift so that your amplitude becomes a function of your shift z. Okay, and in fact, moreover, at tree level, a of z is a rational function of z. Because tree level amplitudes are rational functions. Now, the first important thing to check is that this shift preserves the momentum conservation condition. Okay, and I'll do the calculation on the top of the next board because I know I'm running out of room.
If you ever want to use the bottom of this board, you can move it up.
Oh, right. Ah, right. Thanks, Oliver. Yeah. I am just going at lightning speed through my Blackboard space. Okay. Momentum conservation says I've never written it in any of my formulas, but you know that secretly in front of every scattering amplitude there's a delta function that enforces overall momentum conservation. When we write that in spinor helicity variables, after we shift, okay, well, there are two things here that get shifted, so we're going to get two extra contributions. The first contribution, when we shift from doing the shift of lambda 1 tilde, we get that. And then from the shift of lambda 2, we get that. And these precisely cancel out. So we stay on the locus of the momentum conservation delta function. Okay. Now, the amplitude we started with is what we get if we set z equals 0 in this one parameter family of amplitudes. And by complex analysis, we can write that as a contour integral over a sufficiently small circle around the origin. Okay. A of z certainly has no pole at 0. That would be pretty bad. That's the amplitude we're studying. It has a finite number of poles. Any tree-level amplitude for a finite number of particles has a finite number of poles. So there's some pole that's closest to the origin, and as long as we make our little circle closer to the origin than that pole, then we're fine. But now, of course, we can close the contour the other way, push it off to infinity, so I'll write here equals by pushing the contour out to infinity. When we do that, we pick up contributions from every pole. So if you imagine this is the z-plane, and here's the contour we start with, and there will be poles at various places. We move that contour outward, and every time we cross a pole, we get a contribution from the residue of that pole with a minus sign, because we're going outward. So we get minus the residue, sum. Let me put a sum of residues. And then possibly we get a boundary contribution from infinity. This boundary term will vanish if a of z goes to 0 as z goes to infinity. So this obviously is false in some theories. For example, if you had a scalar field theory with a 4-point amplitude that's just some constant lambda, you can shift all you want. It's not going to go to 0. It's going to be constant at infinity. So certainly some field theories have boundary terms, But many field theories of great interest do not have boundary terms. We will see, for example, that the scattering amplitudes you get for massless spin 1 or spin 2 particles do not have these boundary terms. So I'll put absent in Yang-Mills and GR. Yes?
How do you know you don't have any branch cut or?
Good. The question was, how do you know you don't have any branch cuts? And again, here I'm relying on the crutch of perturbation theory, and I'm relying on the fact that at tree level, I know every scattering amplitude can only be rational, a rational function. Okay. Any other questions? Okay, so let's ask the question, where are the possible poles that we might encounter? And we already know the answer to that question because the poles occur when the amplitude can factorize. So let me draw a schematic picture here. So so basically what's going to happen is the poles will arrive from there's a graphical rule for understanding where the poles arise, and you can think about it in terms of factorization. Let's call the momentum flowing through here pi of z. So specifically, pi of z is the sum I equals 1, well, I'm sorry, let me write I in I, pi, where I is any subset containing 1 but not 2. Let me comment on that. That goes back to this step of the proof up here. If you have P1 plus P2, and if you shift P1 plus P2, it's unchanged. Right? We already saw that up here in that little exercise. So you won't get any, if particles 1 and 2 are on the same side of this diagram, then the momentum flowing through here will not depend on z. So you can't possibly have a pole in z from such a diagram. The only way you can have z dependence in this propagator is if particles 1 and 2 are separated. So what we're going to consider is any factorization where some subset of the original n particles are on the left, the complementary subset is on the right, and importantly, 1 and 2 are separated from each other. So pi of z is the sum I in I Let me, yeah, this is a little ambiguous. So, you know what I'm going to do? I'm going to, here's what I want to do. I want to reserve the notation of P. I want to reserve P, the notation P1 for the unshifted P1, the original P1 in the scattering amplitude I'm interested in. So this is only going to be a function of z after you do the shift on P1, in which case you'll get an additional contribution, which is what I want to write here. Remember that the shift, I've erased it now. Remember that the shift looks like this. So P1, which is lambda 1 tilde, after you shift, turns into lambda 1 tilde plus z lambda 2 tilde, which is lambda 1 tilde plus z lambda 1 lambda 2 tilde, which is P1 plus z lambda 1 lambda 2 tilde. So in other words, the shift takes P1 to P1 plus z lambda 1 lambda 2 tilde. And that's what I've indicated here. If this subset capital I contains particle 1, then it picks up a shift precisely in this amount. So we will get a pole in Z when Z is such that pi squared is equal to 0. That's by the factorization theorem for tree-level amplitudes, that the only places you get a pole are when an intermediate, when you have an intermediate propagator going on shell like that. Okay. So using this formula, first I get this, pi squared. Then I get the cross term. And then I get the square of this. Now, the square of this is 0 because this is a null vector. Remember the notation, the notation is that anytime you have something that so factors into a product of a two two-component spinners, then it's null. So we get to 0. Yeah, there's a question in the back. Thank you. Yes. Z on the cross term. Okay, let me call this thing pi squared. So when I write this without indicating an argument, what I mean is the sum of the original unshifted momenta. And then for this we introduce a notation. This means, if you want to work it out in gory detail, if you want to put the indices in, Okay, that's what that formula means. Let me put the z in front of the 2 for a reason you'll see momentarily. And this thing, we give it a more compact notation. We call it 1 pi 2. This notation is meant to evoke the fact, so anytime, it's basically like Dirac bracket notation, but anytime you see a square bracket here, that's telling you you have the corresponding lambda tilde. Here's this lambda tilde. It's implied that indices are always contracted with epsilon symbols. This angle bracket of 1 indicates the presence of that lambda 1, and then sandwiched in the middle between the two is this quantity, which carries one of each indices, one dotted index and one undotted index. So we have that. And then by convention, it's useful to pull in a factor of 2 into that definition. Okay. So there will be a pole at zi is negative pi squared over 1 pi 2. There will be one such pole for every subset I that contains 1 but not 2. Okay, and now I'm going to avail myself of this little space, and when I'm done, I'll push it to the top. Let's calculate the residue. By factorization, we know that near this pole, the thing we're supposed to look at is this. This is the quantity whose residue we're supposed to calculate. There's 1 over z out front. Now we know by the factorization that the behavior of our amplitude near that pole, or a pole of the type we're discussing, should be a left times a right, where a left and a right are the amplitudes associated with the left and right blobs in that figure over there. And by the way, it's absolutely crucial that those are individually are well-defined scattering amplitudes. See, in general, if we were drawing a Feynman diagram, the momentum between the left blob and the right blob would be off-shell. So neither blob would actually be a scattering amplitude. But the residue at this pole has the remarkable feature that it precisely places that propagator between the two on shell. So both the left blob and the right blob are legitimate scattering amplitudes. Now down here we have pi of z squared, but we've just seen that this thing behaves as pi squared minus 2z, minus z Okay, now I'll move it to the top. Oops. Okay. So here's an exercise. Calculate or show that the residue at z equals a over b of 1 over z minus ab. Sorry. A minus zb is minus 1 over a. Okay, that's the form of what we have here. We need to calculate the residue of this thing at that pole. So, now what I'm going to do is plug into this formula. This minus sign is going to cancel that minus sign. And I apologize, I have to obscure this for just a moment. But the conclusion is that the original scattering amplitude we started with, that's what's on the left-hand side of this formula, is equal to the sum over all I times 1 over pi squared. This factor coming from the residue. And this should be interpreted as a literal multiplication. So the value of this scattering amplitude times the value of that scattering amplitude summed over all possible subsets where 1 and 2 are separated. Okay, are there any questions about this? Yes?
Why do processes where 1 and 2 are on the same block?
They don't, yeah, so first of all, I mean, the question was, why do processes where 1 and 2 are on the same side not contribute? First of all, implicit or hiding underneath your question is, that sounds crazy, right? If we were doing Feynman diagrams, obviously we would have to include Feynman diagrams where 1 and 2 are on blobs on the same side. So what's really remarkable about this is that this is showing that the information contained in Feynman diagrams is highly redundant, because you can get away with constructing a complete formula for the amplitude that does not need to know those Feynman diagrams at all. Okay, and that should be no surprise, because you know that individual Feynman diagrams are highly redundant, especially in gauge theories. But even very generally, they're highly redundant, and so it just happens that all of the information is contained only in this subclass of amplitudes, and this factorization exposes it well. But to answer mathematically how it happened, let me remind you how it happened. We had this formula, and diagrams where 1 and 2 appear on the same side, they just don't have any residue. They don't have any pole in z. Now, of course, an important point, and I'll get to this in a minute, there's nothing special about 1 and 2. You could choose particles 17 and 35 and do your recursion using those two. Then you would have a sum here over all partitions where particle 17 appears on one side and particle 35 appears on the other, and they remain separated. So there's nothing special about 1 and 2, but what is remarkable is that there are these many different subsets of Feynman diagrams that individually contain all of the necessary information. And this is one way of exhibiting that fact. Are there any other questions? Yes?
Can you use the fact that you can choose, in this case you chose 1 and 2, maybe in another world you choose 2 and 4?
Yeah.
Can you use that redundancy to extract more information?
Yeah, so in fact, I was good. Okay, so I don't know if this is the best time, but I can't resist. Okay, I can't resist because I'm going to need this blackboard. So here I had written two formulas for the scattering amplitude, the 6-particle scattering amplitude 1, 2, 3, 4, 5, 6. I had written two formulas, each of which is individually rather complicated. And these two formulas can be obtained. This is a recursion. So you feed in lower point amplitudes to build higher point amplitudes. So there's an enormous amount of choice. At each step of that recursion, you can choose to change which two spinners you're doing the shift on, right? It's your choice. So there are many different ways you can arrive at different looking formulas for the same scattering amplitude. Here's an example where I intended to highlight this point. These two formulas look absolutely nothing like each other, and there's a whole science between trying to, unless you interpret mess to equal 1/2 of the right-hand side, okay. But, okay. There's a whole science between understanding the identities that allow highly, highly non-trivial functions of the kinematics to become equal. And I'll get to that a little bit later in this lecture. Okay. All right. I do want to say, let's see. Good. I want to make one comment that in gauge theory, with gauge group SUN, we can use a useful trick called color ordering. And that allows us to dispense with these FABCs. Now I'm just going to make the claim. It's rather trivial to prove, but let me state the claim. Any amplitude for n gluons can be written. Now, because gluons are bosons, this scattering amplitude should be fully symmetric under the exchange of any two of the particles. So I'm now going to write it in a way that makes it manifest that it is symmetric. Any amplitude can be written as a sum over all permutations, otherwise called Sn, the permutation group on n letters, of something that we call the color-ordered amplitude. I know the notation is ambiguous, but don't worry, because in the future I'm only ever going to use this thing. Sometimes it's called the color-ordered sub-amplitude times a product of traces of generators of SUN. Thinking about these amplitudes this way is natural if you think about open string amplitudes, where open string amplitudes are specified by a particular ordering of the vertex operators around the disk. Okay, it's very analogous here. You imagine, so the important point is that, and this is sufficiently important I should write it. A 1 through n can be computed by summing only planar Feynman graphs with the indicated ordering of the external particles. So just to be absolutely clear what I mean by that, okay, this is a perfectly fine Feynman diagram. This is a perfectly fine Feynman diagram for 6 particle amplitudes, but it does not contribute to A 1, 2, 3, 4, 5, 6. Because the ordering, it's incompatible with that ordering of the external particles. I won't have more to say about this. It's just important because it's a useful bookkeeping device that I may occasionally refer to. Yes?
Planar, you only need planar if you're doing tree-level diagram.
That's right. Yeah, so that's an important point. So I'm not taking the question was I only need planar because I'm doing tree-level diagrams. This particular application of planarity has nothing to do with large N. I mean, large N is a tool that we use often, but this is just a statement that any any tree-level Feynman diagram can be made planar with respect to some ordering of the external particles. Although if every Tazi lecturer is allowed a 1-minute diatribe on their pet peeve, I hate planar graph, okay? It's fine to say planar Yang-Mills theory, but when people say the word planar graph, 99.9% of the time they mean plane graph, right? A planar graph is one that can be embedded on the plane. A plane graph is an embedding of a planar graph onto the plane. A given planar graph can have 17 different plane embeddings. If we were doing phi cubed theory, we wouldn't care. That would be one Feynman diagram. But if we were doing Yang-Mills theory, those would be 17 different contributions. Okay. That's the end of my diatribe. Exercise. Okay, this exercise is considerably harder. Use recursion to show that in Yang-Mills theory, these are actually not hard to show using recursion, okay? Whenever I ask you to show that something's 0, it's pretty easy because you set up the recursion and you find the right-hand side is always 0. So the less trivial thing to show is that the first case you get something non-zero is when you have 2 negative helicity gluons.
This is all n greater than or equal to 4?
Yes, that's right. Oh, thank you. That's an important qualification. This is all n greater than or equal to 4. There's a special case. The 3-particle amplitude is a special case. Okay. And the sort of conjugate amplitude where you have only 2 pluses looks like that. Okay, now I'll raise this board so everyone can see it. Oops. Okay.
So these amplitudes that have only 2 negative helicity gluons are called MHV. That stands for maximally helicity violating. And these are called MHV bar.
Mark, just to check, are I and J in the denominators or not?
In the third formula or the fourth?
Either one. There's sort of
Oh.
special.
Yeah. No, so in the denominator are all the cyclic 1, 2. Yeah, I should have made that more clear. 2, 3. So 3, 4. So if I and j are next to each other, then this will cancel one of the terms in the denominator, and that will become a cubed. But I and j don't have to be next to each other. They could be far away from each other. Then there's no cancellation, because the denominator only has the adjacent ones. Are there any questions about that? Okay. By the way, all of this of what I'm doing now is highly motivated by Pedro's talk yesterday, because where I'm trying to get to is to be able to phrase the question of what is the kinematic space for supersymmetric Yang-Mills theory, a problem that is not yet completely solved in the literature, and is a very interesting problem. Okay. So the next thing that I need to introduce, I've introduced the bookkeeping device of color ordering, very vaguely. Now let me introduce supersymmetry. So tree level gluon amplitudes are insensitive to supersymmetry. They're the same regardless of whether your theory is supersymmetric or not. And that's just because a tree level amplitude has no loops, and the only place, if you have only gluons on the external lines of your amplitude, there's no way you could possibly have any fermions or anything else in your diagram unless it appears in a loop. But if we're looking at tree level, we'll never see that. So we may as well generalize to n equals 4, which is the largest supersymmetry algebra in 4 dimensions that does not have particles of helicity greater than 1. So the states of this theory helicities plus 1, that's the gluon, plus a half times 4. There are 4 fermions with helicity plus a half. Helicity 0, 6 scalars, minus helicity 1/2 times 4, and then there's the negative helicity gluon. So there's 16 massless states. Okay. A convenient bookkeeping device for handling this information is afforded by using superfunctions or using Grassmann variables to write down generating functions that encapsulate many different component amplitudes simultaneously. So we introduce 4n anti-commuting variables. That means Grassmann a to I a runs from 1 to 4, and I runs from 1 to n. And then we introduce a super amplitude which is a function of lambdas, lambda tildes, and etas. Now, any function of Grassmann variables has a finite Taylor series expansion. So let's look at that Taylor series expansion. The Taylor series expansion has up to 16 to the n terms, but by far most of them are 0. Let me just indicate how it works. Okay. The first term in the Taylor series expansion has no fermions. And that, by definition, will multiply the amplitude where all particles are positive helicity gluons. Now, we know that's 0. I've told you that's 0 on the other board, but just for the sake of pedagogy, I'm explaining to you that this amplitude lives in this component of the superfield expansion of our superamplitude. Okay? Then we can have terms that are linear. I mean, I'm going to be here all week if I go all the way up to order 16 to the n in the superfield expansion, but I'll stop soon. Next, we have terms that are linear so we could have some eta ia times the amplitude where everybody is a positive helicity gluon except for particle number I, which is 1 down in helicity. So a plus a half helicity fermion of type A. Remember, there are 4 of them. So I'll explicitly write here plus 1/2 helicity fermion of type A. Okay. Now, just to indicate, at next order, you can have 2 types of terms. If you have the same index here, that indicates that particle I is a helicity 0 particle that is a scalar of type AB. Now, because A and B are anti-symmetrized, there are 6 of these. So 6 anti-symmetric choices for AB. Those correspond to our 6 scalars over there. Over here, if we have different particle indices, this would be particle I being a plus 1/2 helicity fermion of type A, and particle J being plus 1/2 of type B. Now you can go all the way down the superfield expansion, down to the very last term, which is product of all 16n etas times the component amplitude where everybody is a negative helicity gluon. Okay. So we'll see this in action. Ha, that's a joke. We'll see this at work when we do some examples, but are there any questions about how the component amplitudes? So this is useful for several purposes. In just a minute, I'll show you how you can manifest supersymmetry. So the fact that this theory has n equals 4 supersymmetry implies that the different amplitudes, all these different amplitudes, are not independent. They can be related to each other by supersymmetry ward identities. And adopting a manifestly supersymmetric notation is one step closer to being able to make all those relations manifest. It doesn't manifest all of them, but it's an important step. Now, the n equals 4 supersymmetry algebra has a bosonic SU4 R symmetry that acts on our A indices. Okay. Scattering amplitudes must be invariant under this SU4 symmetry, so only terms with number of etas equals a multiple of 4 can be non-zero. Like this second term here, I immediately know that it's 0 because there's no way to form something that's SU4 invariant with only a single index. Let me be explicit. You can only form SU4 invariants using epsilon A, B, C, D. Okay, so you need to have a number of indices being a multiple of 4. So therefore, A splits into So when we do our Grassmann-Taylor expansion, we'll have terms with 0 fermions. Then we'll have terms with 4 fermions. Then we'll have terms with 8 fermions, 16, etc. All the way up to, and now I see I made a mistake here. This shouldn't have said 16 n etas. I was confusing with that 16. There are only 4 n different etas. That's even written up there in the very beginning. Okay. Okay. Now, how can we manifest supersymmetry? Well, the appropriate representation of the supersymmetry generators in the variables I'm using looks like this. Okay. You can just tell by looking at this that the anti-commutator of Q with Q bar is going to give you lambda lambda tilde, which is P. That is the supersymmetry algebra. So in particular, we can manifest, well, let me write it this way. We know that momentum conservation implies that every amplitude has a delta function So how can we manifest supermomentum conservation? If every amplitude contains an overall factor I should clarify here. In this formalism, it's become necessary to treat half of the supercharges differently from the other half. So we can only, in this formalism, only half of the supersymmetry is manifest. So I'm going to clarify that by specifying that I want to make the Q supermomentum conservation manifest. The Q bar supermomentum conservation will not be manifest. And that's a very interesting story that I won't have time to discuss. Okay, this is an 8-dimensional delta function because A takes on 2 values, little a takes on 2 values, and capital A takes on 4 values. And so the point is that this is annihilated by the total supermomentum operator right here I've written an expression for the Q and Q bar generators as they would act on a single particle state. But if you want to act on an n particle state in the Fock space, the relevant operator, just like it's the total momentum that's conserved, the relevant operator acting on an n particle state is the total supermomentum operator, which is the sum. Now, the point is simply the following, that this operator obviously annihilates that operator just by the properties of fermionic delta functions. Oh, I am. Thank you. I would not have noticed. Okay, that's an excellent place for me to end then. Except one more comment, which is that we can't have terms with less than 8 fermions or less than 8 etas in the expansion of our superfield. So I'll pick it up from here next time. But earlier we saw that our superfield expansion, our super amplitude has an expansion with 0 fermions, 4 fermions, 8 fermions, etc. But in order to satisfy the demand of supersymmetry, any terms with 0 or 4 fermions have to vanish, and the first we can have is 8. Okay, so I'll end it here, but open it up for maybe one question if there's time. Okay. Yes?
While doing BCFW, we had a boundary term. What are the assumptions that goes in to drop it? For example, if you have higher derivative gravity, can you drop it?
It's in general, it's a thing you have to check on a case-by-case basis. Thank you. In the BCFW recursion, there was, in general, a boundary term. And the question was, would it be present, for example, in higher derivative gravity? So it's a thing that you have to check case by case for the theory you're working in. As I gave the example in scalar theories, there is a boundary term. In pure Yang-Mills theory and in pure gravity, there's no boundary term. There are many other examples of theories without boundary terms. I don't know the answer to your specific question. It might be possible to look it up in the literature, or it would be something you would have to check.
But is there any nice physical understanding of which regime of scattering amplitude determines this term?
Yes, it's essentially a high energy limit, but it's a high energy limit in a particular complex direction, because taking z to infinity is like taking some particular strange high energy limit of an amplitude.
So roughly like Daisy?
Yeah. So, any other questions? Yeah.
I see the question. Because encode 4 is from Lagrangian, we know it's CFT.
Mhm.
And the symmetry can only define trivial and scalar amplitude, but get away non-trivial stuff.
Ah, yes, yes. So n equals 4. So sometimes I answer that question as a joke, which is only partially funny, which is to say that this whole research program is the whole aim of this research program is to find the most beautiful, mathematically beautiful ways of writing the number 0. But n equals 4 Yang-Mills theory has a very special property that I won't be able to get to in my lectures, which is that amplitudes are exactly equal. There's an equivalence between scattering amplitudes and Wilson loops. I will have something to say about that in my next lecture. And because Wilson loops are well-defined observables, so therefore, if you want to, you can imagine that I'm giving my entire series of lectures on Wilson loops. And you can define, for example, infrared well-defined quantities by taking ratios of Wilson loops, or equivalently ratios of amplitudes.
All right, let's thank Mark again.